Yes, I bought I think 3 packets, no, 5 packets. Thanks for the food. No, but unless you put it on the
用过 IPMI 的研究。
I love that like
Because one or two students what is it? Oh, good. Yeah, so I got
So I have one copy, and they have one copy, and you as a math instructor. So they can get it different.
哎呀，我刚才去试了一下，
挺好的。你唱出来的味道不对。
Because that's our fund. Any grad they're all
I forgot about it.
Joseph while they're
What is it?
Oh, well, I'm gonna see if I can get them.
What did you get?
I just know that where is located. No, you just need to search for
No, because if you're the type of person, like, you can pay attention and then just look at the notes. He does take notes. But like, I prefer to write notes. He's already on the next room, and I'm like, like this one, you know, this one, he does it like this so fast. Sure. But I know it's 6 seconds of the time. But he's going too fast. It was a 6 month. Because it was inside a snake. And it was a 6 like that so fast that it looked like. These are the two symbols. It's a less than and less than. Bro, you're writing fast. They mean totally different things. Yeah.
I want to ask why you use days. Like Monday. No, Monday and Friday. We don't have Wednesday. But it's written on that paper that it's Monday. That's why you're shocked. Like, why is she? No, Monday, Wednesday. Oh, no, Monday. Friday. She has only 3 days. You have 2 days. Yeah. I have 2 days. How many students in your lab? 7. Each? No.
I think that's
Total?
But over here,
You know, last time we had to.
I didn't take Dr. Torres and take it for me.
No, the last lab we had to solve the quadratic. It's so annoying that time.
no number one,
I took it. The lab, like lab is 50 minutes, 50 minutes. Like I took
but I don't want to do that.
every single lab 1 hour.
I put a note.
Because they don't even understand how it's going.
I was like, look at your
How can it done?
like that.
How can they solve for the quadratic formula that's no, because
Okay, let's start. Thank you everyone to come here on this Friday afternoon to enjoy our first seminar in this semester, supported by both Department of Mathematics and the Division of Data Science. Today we are happy to have Dr. Dao Nguyen to visit our campus. And Dr. Dao Nguyen is an assistant professor in the Department of Mathematics and Statistics at San Diego State University, California. He previously, before he joined SDSU, he previously served as an untenure-track assistant professor at the University of Michigan. And he earned his PhD in mathematics from Wayne State University. Dr. Nguyen's research focuses on optimization, data science, and control theory with applications in engineering, medicine, biology, economics, and related fields. So he has very broad research interests in different kinds of applications. And also he is the author of the book Foundation of Machine Learning, which is currently supported by NSF grant. And he has published many papers in high-ranking journals, including Science, Journal on Control and Optimization, and the Journal of Differential Equations. And he also served as a guest editor of Journal of Optimization in Theory and Application, right? And he also received multiple outstanding academic achievements awards. And let's welcome Dr. Nguyen.
Firstly, I would like to say thank you for the organizers for organizing this wonderful meeting, and thank you for all the audience for taking your time to be here today. And today it's my great pleasure to present the talk related to optimization using model predictive control combined with iLQR and neural network. Because I don't have the pointer, so maybe I'm gonna use just this one to move them.
Here.
Yeah.
Is working.
Is it working? Oh, thank you so much. Yeah, wonderful. So I can be anywhere I want now. Yeah. So firstly, I would like to mention a little bit about. Can I move? Oh, I can move back and forth.
Oh, you can't move.
Yeah, you know. And let me use this one instead. Then. So firstly, let me introduce a little bit about the history and the introduction of optimization problem in some applications for this model. After that, I'm going to move to the main tools where we need to use the model predictive control and also iLQR and neural network for this problem. And I'm going to show you some applications and some options in the future. And please feel free to interrupt me at any time during the talk if you have any questions. Okay, just raise your hand. Yeah. Thank you, everyone. So let's get started. Hi, Jerome. So actually, optimization in optimal control has many applications in the real life. For example, in mechanical and electrical engineering, mechanical impact, Coulomb friction, diode and transistor, human and resource, etc. And we have some applications that we published in robotics. For example, we want to minimize the distance from, I'm going to bring the robot here. Like we have the, we can minimize the distance from the starting point to the target while avoiding all the obstacles on the way. And we can minimize the energy of the robot as well, even the velocity of the robot, to make sure that we will find the shortest path to the distance, to the target. And then we can have some application in chemistry. For example, we do some application related to nanoparticles in the straight circular capillaries. Also in medicine, we published some paper related to brain cancer, minimizing the beam delivery time to detect the tumor in brain cancer. And in economics, you can do something with, have you watched the movie Nash, The Beautiful Mind? Yes, right? No, not yet. If you have watched that one, you know, like Nash equilibrium. So it's kind of the point where both like firms and customer, they can reach the balance point where both can get the benefits, right? And the optimal benefits. So in this case, we can do some optimization about Nash equilibrium, or we can also have minimizing the risk or maximizing the profit of the company. So those are like some applications that we have done in the past. And if you are interested in any of the projects, please feel free to contact me or Dr. Wei or or other faculties here. We are happy to help you and provide you more information about the projects, and we can collaborate in the future. So let's go to the problem formulation. Actually, in this case, we would like to find the optimal control and optimal trajectory with the minimal cost. Because basically, for the optimization problem, you can consider the cost functional with some constraints. We can have equality constraints, inequality constraints, or geometric constraints. And then we can have the dynamical system where your velocity will be controlled by a dynamical system. And regarding to the dynamical system, you can have normally if you do equations, dynamical system, you can have a lot of algorithms using neural network or like machine learning, data science stuff. But if you use differential inclusion, it's going to be more complicated. And I'm going to show you some of the methods that we can think about when you do with the differential inclusion. So in this case, the first method that I would like to introduce is the well-known MBC. MBC here is model predictive control. And if you want to use this one, you can find the ways to reduce computationally complexity and increase the effectiveness of the problem. And we can consider the main formulation of the problem here. So the first one is the cost functional, or sometimes you can call the loss function, right? You want to minimize that one. The first term is the second term is the terminal cost. The first term is the running cost, and you can see capital T here is the given time, right? We have X here is called the state variable. Y is the control variable. And we can discretize why do we have little k there. That means, for example, if you have the continuous path, right, for the continuous function x of t, you can discretize it. And this is the time. We have the value of x at the time t0, we can denote it as x0. The value of x at t1, you can denote it as x1. And similarly, you can have xn, xk right here. So that's how we can discretize the problem. Similarly for u, if you have some properties for the state variable, normally in the real life you can have the absolute continuous function for x, and for u it's going to be the measurable functions. In some other papers in the literature, you can see that we have a lot of absolute continuous function for the control function, but in the real life, maybe when you consider we turn on and turn off this switch, right? Then the velocity of the switch will be 0, 1, 0, 1 like this. So it's going to be the piecewise constant function. It's not going to be the continuous function. So that's why if you want to do with more applications in the real life, you can proceed with the measurable functions for you. And we have the first constraint here is called, we have xk plus 1 equals fx xk uk. That's going to be our dynamical system, because it comes from x dot equals fxu, for example. There are some papers that we published. We will do it with with x dot belongs to capital F of xu, and this one is going to be a mapping, so it's more general. And then when we reduce it to the specific case, it's going to be x dot equals little f xu, where f here we can do it with the if you have this part is non-Lipschitzian, if it's non-smooth, if this part is highly unbounded, then how do we do it? We will use the method, discrete approximation method, to solve it. And if you have x dot equals f of xu, there are a lot of methods that we can use here. We can use MBC, we can use iLQR, we can use quadratic programming, or there are a lot of other methods like in data science. For example, you can try to use neural network for that one. And for the second constraint, we have gk of xk uk equals 0 and hk of xk uk greater than or equal to 0. Those are two inequality and equality constraints. Sometimes if you want to have the open question, you can add the geometric constraints there, and it's going to be more complicated. And if you use geometric constraints, then you have to use a method of generalized KKT to find the necessary conditions, and then after that you can find the optimal solutions for that problem. In this problem, since I'm gonna introduce the model predictive control method, so that's why I try to reduce all the assumptions of this problem to the simplest case. And after that, like, we can see like more open questions later on. Yeah. Any questions so far, everyone?
So the capital F and the small f means that capital F is a family of functions, right?
Mm-hmm. Yeah. So in this case,
so it will be indexed by a certain parameter, or
so in this case, actually, if normally we do it with the one that we publish, it's called like this is the mapping, and then we have the perturbation. In this case, the meaning of this one is, well, this is called the normal con, and the whole mapping here is non-Lipschitz, unbounded, and we can have this function it is a non-smooth function. And the way that we do it is, when you have smooth function, you can normally if you want to find the optimal solution or the minimizer in real analysis, you have to find the critical point, right? So in lower dimension, you have f prime of x equals 0. You solve for that. But what if you cannot calculate the derivative of that function? So what if I will give you a non-smooth function? Then we will think about like subdifferential. Instead of taking the derivative, there is some way for you to take to do that. If you have f of x equals absolute value of x, right? Then you cannot take the derivative of that function. Then we will think about the new definition. It's called and then you can see some tools in variational analysis to solve that problem. And then we have that's the first thing for the non-smooth, and for the unbounded. For the unbounded, you can use some Weierstrass theorem. And then for the convexity, if it's not convex, you have to convexify that problem first, and then you can solve for that. Because if you do it with the convex problem, then you can find the optimal solution. Right? Yeah, so those are some tools that we can use for this model. I hope that I answered the question. Yeah, thank you so much. So in this case, we will do 3 steps. The first one, we will predict future system behavior over a finite prediction horizon. What does that mean? It means, for example, if you consider the sequence X, maybe I'm gonna have another figure later on to explain the method carefully. And then the second thing, we have to solve optimization problem at each time step, and then we use receding horizon approach to find that one. This is the next slide where I have the diagram to show what is the model predictive control. So we have xk. So at the beginning, we are given the initial data x0 equals x0, and then after that, we can measure the current state x0, and then we can predict the future state over horizon n using the dynamical system. For example, in this case, we have xn plus 1 equals f of xn un. So we can use that one to calculate xn plus 1. And then we can, at each time step, so let's look at the horizontal direction here. At each time step, you can solve optimization problem and find the control for each time step. And then after that, we can find the first control input UK. When you can find the first control input UK over there, I think it should have the pointer, so I can show it on the, oh, here, yeah, that's right. So in this case, where we, at each time step, this is S time step, the first time step, right? You can solve the optimization problem and find UK. And then we apply the first control input UK. You can shift it, and then you can move it forward in time, right? You can predict the next xk plus 2, and then you can solve for the next optimization problem and find uk plus 1, and so on and so on. So that is how we use the model predict control in this case. In the next slide, we can select the prediction horizon. P is P is very small. Why do we need to do this one? When we measure the current state time at each sample time little t, then this is the heuristic approximation of the function, the terminal cost. And we have the running cost here. In this case, you will calculate it up to tp minus 1, and tp is denoted by minimum of t plus p, capital T. After that, if if you calculate this one, it's kind of like when you work with the difficult problem, you try to discretize it, and we solve the smaller problem from the infinite dimensional optimization problem. If you can reduce it to the finite dimensional optimization problem, it's going to be easier. And then we solve for that one. Then by choosing P is very small comparing to T, then the computational cost is going to be reduced. Okay. Then normally the MDC problem in this case will be formalized as the we can do it as a quadratic programming with some linear constraints. If it's non-linear constraint, I'm going to give you some tools to do that one. And this is the standard form of the quadratic program, right? We minimize this cost function or subtract to the inequality constraints. Gz less than or equal to W, where H here is the Hessian metric of the objective function here. I'm going to move to the next slide. And to solve that, we use this is the pseudocode of the MPC implementation using QB solver. If you need this one, I can share it with you. Basically, when we use QB solver, we convert the input into desired form, and then we cross over from CVX of opt. We return the optimal control variable U0, and then we can use MPC simulator. In this case, if you store, like we use the loop for zero from I from 0 to the end of the simulation, we can store the optimal xi ui here, and then we update xi plus 1 using the dynamical system like we discussed earlier. And then we end the loop here, then we can find the list of all the data for the possible output, xi and ui. Then next, although QP solver produces the exact solution, but due to the high computational cost, so the conditions it demands, in this case, like we turn into some methods that produce the approximating optimal solution and have a faster convergence rate. Actually, to improve the accuracy as well, we will think about iLQR in this case, and then we can use iLQR to handle some non-linear dynamics. If you have linear dynamics, we know how to solve it, but if you have the non-linear dynamics, you can think about iterative linear quadratic regulator or iLQR. And if you use this one, you can apply to the real-time. This is real-time applicable and computationally cheaper than the full non-linear optimization problem. Also, it produces optimal feedback gains and enhance the robustness of the problem. So we can apply it for robotics, autonomous driving, or we have some paper about traffic flow model, crowd motion model. Like everyone wants to go to the exist, and then we will try to solve for that problem. It was developed by Benel. She's a French mathematician, and that problem started with like, okay, everybody will be inside the room, and we want to find the shortest way to get exist when we have fire or something. And then you can use also like bi-level sweeping processes for that one. That means in this case, if this is our group, there is another group right here in all the groups, right? So in this case, the bi-level problem means that we have to separate it into two different problems, the upper problem and the lower one. So for the upper problems, we will have the non-collision between all these groups. They will find the shortest path to the target, but they cannot overlap each other. There will be the non-collision condition between all the groups. In the lower problem, in each group, like the two people cannot overlap each other as well. So these are like the bi-level optimization problem. And if you want to use non-collision condition to formalize the problem, then you can use the mathematical problem called you can use normal cone. The reason for this notation is if you have the hidden constraint x belongs to C, then it means that it is equivalent to the non-collision condition. That means like all the two robots cannot be overlap each other, or we don't have the collision condition. And then you can control the velocity. I can draw the picture to explain this one. Assuming that you have a ball inside the ring, right? The ball we have to make sure that when the ring starts to move at the time t equals 0, the ball has to stay inside the ring. If it crosses the boundary here, it means the collision happens. So in that case, the velocity of the ball has to point inward the interior of the ring to make sure that it will stay inside the ring. And in that case, I'm going to draw the picture of the normal cone to, let's say this ring is going to be the set C, and this is X. So the normal cone of the set C to the set C at the point X is going to be this line from here to here. I'm going to use the blue color then. We have, this is the normal cone. And the velocity, negative velocity, if it belongs to this direction, right? That means that means in this case we don't have the collision. The reason is the velocity of the ball will point inward the interior. Because negative, we have to put negative here. Negative x dot belongs to the normal cone. Then we don't have the collision anymore, right? So this is the physical meaning of sweeping process. And one thing it sweeps, and one thing it is swept. This is it sweeps and it is swept, right? Okay, so that is like some of the methods that we can use here. And let me discuss a little bit about iLQR so that we can use it to improve the accuracy and the robustness of the problem. How do we do that? Firstly, when you use MPC, you know that we must measure the current state, and then we have the initial gas trajectory x0 and u0 here. Before finding the optimal control sequences, u1, u2, u3, by solving each optimization problem at each time step, you will need to use iLQR solver right here. Because when you use iLQR solver here, we can linearize the dynamics. Can you see it from the back? Can you please confirm it? Yeah, okay. Because it's very small, so I'm worried that we cannot see it clearly. Here we have the quadratic approximation of the cost, and we solve the LQR problem here. We update the trajectory, and then we can check the convergence. So that is the iLQR, what iLQR solver does in this step. And then when you find the optimal control sequence, we can apply the first input to the system, and then we can solve for that one. And then repeat that one again to do it for the next step. Just repeat that again and again for the loop. Now I'm going to introduce a little bit about the iLQR. Have you heard about forward-backward algorithm? So for forward algorithm, we need to initialize with initial state x0 and initial control sequences like u0, u1, u2 until un, right? And we do a forward pass. That means we will simulate the system using x0 and the sequence of control u to get the trajectory to get x1, x2, x3, and so on. And then after that, we do a backward pass. We estimate the value function. So in this case, we will minimize the cost function. Or sometimes we call cost functional. It depends on our problem, right? Cost functional is different from cost function. Because like if you have the function of function, right? Then you have cost functional in this case. And we have, if you do, we estimate the value function in dynamics for each xu in the state space and control signal trajectories. After that, we calculate an updated control signal u hat and evaluate the cost of trajectory resulting from x0, u0. Basically, in this step, you want to find the minimal cost function. If it's, if this step, we assume that this is the minimum cost, right? But the next step, you can find, there is another cost function. It's less than the cost function in the previous step. Then you will reset it for the new cost functional. And then you keep doing that again and again. to find the minimum cost. Here, this is the backward pass. We can express the optimal action in terms of the state. This is, okay, there are so many words, right? So let's see the figure, maybe it's going to be easier to see. For the forward pass, here we have x1, x2. We have x1, x2 is going to be f of x1, u1. And then u1 will be calculated from the, wait, we have x0, right? Then we calculate x1 first. And after that we have x1, we have u1, and then we have f of x1, u1. It's going to be x2. And keep doing that, and so on and so on. That's how we do for the iLQR algorithm right here. And if you look at this column, it's going to be the first time t equals 1, and then t equals 2 until the final time t equals capital T. Okay, that's right. I thought that was a typo, but it's correct. Yeah, we plug u1 from the previous because we have capital U. That means that is the sequence that contains U0, U1, U2 until UN already, right? Okay, so the next step, we try to empower MPC with machine learning. If you look at this one, the MPC solver, we have the model and the optimizer. So the optimizer provides the control to the model. And the model, when we predict the next times the xk plus 1 from xk, we will use the model to predict that one, and we find the optimizer at each time step by solving the optimization problem at each time step. And then we can use, from the MPC solver, it provides the control to our dynamical system. And our dynamical system provides the state variable for the MPC solver. In this paper, I'm gonna focus on the second technique and the third technique. That means I'm gonna focus on the machine learning enhanced planar and the machine learning based feedback controller. We have the machine learning enhanced planar provides the trajectory planar, and after that we can provide the trajectory reference trajectory for the MPC solver to solve for that. And this one, it also provides the value for the MPC solver as well. For the third method, the machine learning based feedback controller, we will get the reference trajectory from the trajectory planar, and then we can provide the control to our dynamical system. And vice versa, the dynamical system provides the state to our machine learning based feedback controller. So this is like kind of the diagram to summarize all the things. If you want to use a neural network, in this case, I'm gonna present the method. Firstly, we have to generate the training data. So we discretize the state space. We create a mesh for the time interval from 0 to capital T by discretizing all the time interval. And then we generate optimal control using the iLQR algorithm. Then we will obtain the list of all the states in the corresponding optimal control U. And then after that, we will form a larger data set. After that, compile the results from iLQR. You can develop a set of training data consisting of 3,000 sets of states with respective optimal control inputs. And we can use the cost for. In this case, actually, you can think about the cost function as the mean square error, and you can use ReLU for that one. You can try to construct and train neural network, maybe with what we did with 2 input layer, 1 hidden layer, and you can do with 2 output layers. We can try with that. I can share with you the code if you are interested in this one. Okay. Now I'm gonna show you some open questions. So instead of doing the differential inclusion using the inequality, we can generalize it as the differential inclusion. So it's going to be more general, and we can apply to more applications in the future. And then instead of the equality constraints for the control U, you can do that U of t belongs to a set capital U. And set capital U here is a convex set. And the trajectory is absolutely continuous. The control U is measurable. So we published this one in SIAM tunnel control and optimization. And let me move to the, this is just, yeah. And there are some other open questions that you can, actually these are, with the implication, let me see. Oh, in this case, we published this result already, but if you, there are some open questions. If you convert the cost functional, instead of doing it just for the terminal cost, you can add the running cost, you can add the energy, and we can have the randomness, or you can have stochastic in the dynamical system as well, stochastic process. So those are open questions here. And for the red part here, actually, what I mean is you can control the perturbation. That means you will control the velocity of the ball to make sure that the ball will stay inside the ring. The second paper here, we control the shape of the ring to make sure that the ball will stay inside the ring. The third red part here, that means we control both of them, the shape of the ring and the velocity of the ball, to make sure that the ball will stay inside the ring. So those are some papers that you can have a look, and we can use the discrete approximation method to solve for this one. Let me skip this one and solve the mobile robot model. So this model was introduced by Ramdan Hechai and Masaoud Bonkel, and we can formalize this problem as follows. We have the configuration vector. In this case, x1 here is our robot under the consideration. And we have x2 until xn, they are all the obstacles on the way to the target. And then we can have the x coordinate of the robot, y coordinate of the robot. This is going to be our constraints, because when you have xi minus xj minus 2r greater than or equal to 0, it makes sure that, okay, the center of the safety disk of the robots, when we do the difference, it's going to be greater than or equal to 2r, 2 radius of the robot. That means there is no collision, right? No non-overlapping condition here. And then we can apply our method to see there are, I'm going to show you the simulation right now. This is the simulation. Here. For example, I'm going to show you a specific one with 10 robots, for example. We have an animation here. So for the we are given the initial trajectories, right? And we are given the control, the relationship between all the control and the constraint for the control as well. And if you see, so the trajectories of the robots, once you go to the target in that direction, and there is non-overlapping condition here. They will not be overlap each other. And for example, if the first robot, it starts with, don't worry about the negative control, you know why we have the negative side, it's just like the direction is opposite with the positive direction when we define it. And then the speed is 5, the speed is 4, right? So the speed is going to be, it's going to play the role here. The control for R0 for the robot number 0, so at the beginning it runs very slow, but after that, if it wants to catch up with other robots, it will meet the purple one at the contacting point. So the contacting time is around here. Yeah, that's the contacting time. And then when they meet each other, like sometimes the robot, the first one will push the second one go to the target together. And then we can consider this one with more robots. Similarly, yeah, I want to show you some tools related to. Okay. So this is the specific construction when you train the neural net. As I said, you can use reloads, and then we can have the learning rate of 0.01. Let me see. Okay. The current project, you can consider the general set C and the numerical method for random control sweeping processes. That means instead of the perturbation, it's just the not smooth function or smooth function. You